It's a great pleasure to have the opportunity to give the Eringen Medal Lecture. I'm deeply honored by this. I met Jamal once at Princeton in the 1970s. We had a very pleasant conversation, and he impressed me as a very kind and gentle man. The title of my talk is My 50-plus Years in Mechanics and Computation. It's rather vast, I have to admit, and I really had a great deal of difficulty to try to fit into the time just a few points that I'd like to touch upon and perhaps give you a little bit of insight into my career. So let me begin by mentioning the Eringen Symposium, which will follow, and that will consist of 15 talks if all goes well. And I don't have time to thank all of the speakers individually, so I'll just do it collectively and mention their names: Wajen Gao, Zdenek Bajant, Mary Wheeler, Ramon Codina, Arash Yavari, Yanggang Huang, one of the co-organizers of the symposium, Glaucio Paulino, Mats Larson, John Hallquist, Chad Landis, Tinsley Oden, Arif Masood, the other co-organizer, Pavel Boshev, Dave Benson, and Omar Gatas, all friends and colleagues and collaborators. So how do you give structure to something like this? Well, one way is just to identify the places I've been over the years and say a little bit about each of what went on during those times. So I'll begin a little bit with my initial career move to industry, and then Cal Berkeley, where I did my PhD and taught for a short while, then Caltech, and then Stanford, where I spent the bulk of my career, and then finally the University of Texas at Austin, where I've been since 2002. So I began in industry. I had a degree in mechanical engineering, and I also had a 5-year scholarship from New York State in science and engineering. And that essentially paid for a bachelor's and a master's. So when I got my bachelor's degree, I entered a work-study program at Grumman Aerospace on Long Island, and I interlaced semesters during my master's program and time at Grumman. In fact, over the 2-year period, I only spent about 9 months at Grumman. I was a mechanical design engineer. My assignment was to work on the nose gear of the Gulfstream II, the landing gear, as you can perhaps see right here. Aside from designing the details of the parts, I also designed the 4-bar linkage, all the loads on that, and et cetera. Now, it was very interesting and a very nice experience because I had the opportunity, of course, to work in engineering, and engineering occupied the 2nd floor of an enormous building, a 2-story building. And the 1st floor was manufacturing. They actually built the planes on the 1st floor. We designed them and analyzed them on the 2nd floor. So I saw every aspect of producing a product, and it left a big impression on me. One of the interesting things is there was no computers, absolutely no computers. Everything was essentially done by hand and perhaps with the aid of desk calculators. Another interesting aspect of that left an impression upon me was the integration of design and analysis. I was a designer working at a board, a drawing board, and the analysts, the stress analysts, the weights analysts, they were sitting right next to me. I could almost reach them and just touch them. And so as the design progressed, they would work on the analysis and give me feedback on dimensions of things and things that I would have to think about. And I could go downstairs and talk to the people that actually built the plane and ask them, could they build this, or were there issues? And I get a lot of feedback on that too. So everything actually went very well there. It was a good learning experience. But you want to do it once, maybe not multiple times. So then, after I completed my master's, I went to General Dynamics Electric Boat in Groton, Connecticut, where submarines are built. And I was a research and development engineer. So that was a new experience altogether. And obviously one that had a great effect on shaping the rest of my life. Well, there we had computers, and we had a Univac 1108 with an enormous drum storage device. So this was a supercomputer at the time. And the group I was in was very adept at matrix methods of structural mechanics. And those procedures had actually become sophisticated at that time. They were computer-based, but they were basically structures composed of beam elements, beams, frames, things of that nature. And they were doing calculations of over 10,000 degrees of freedom around 1965, which is amazing in retrospect, given the facilities that were available. Now, in addition to beam-type models, they could model the hulls of submarines, the overall structure, internal and external, by using lattice analogies. And they employed the Renikoff method. So that was something that everybody in our group knew very well. It was developed by Alexander Renikoff, who did his PhD during the Second World War years at MIT. And he further developed that as a professor at the University of Toronto the rest of his life. But the idea was to mimic the behavior of, say, a plate or a shell by a certain lattice construction of beam elements. And it actually worked reasonably well, though there were many restrictions on it. You could only obtain Poisson's ratio 0.25, that was it. So it was limited, it was linear analysis, but it allowed stress analysis of complex shapes. Now, one of the things that I found interesting as I studied the method was that there didn't seem to be any theory associated with the distribution of mass on the structures. They would simply lump mass at selected nodes to more or less distribute them somewhat uniformly over the entire submarine. And I wasn't very comfortable with that. And I was mentioning that to some of my colleagues there. And one of them mentioned something called the finite element method. And obviously those words just had an enormous effect on the future of my life. Well, I got very excited by that. I started reading papers about the finite element method, and there weren't many, and they were very hard to read at the time because it wasn't very clear what people were doing. They all had their own notations and different ideas about what the method really was. And so I talked to my boss and induced him to pursue research in the area. So he started the finite element development group. And the group leader was a young PhD named Henno Alec. And initially, I was the group. And then they assigned programmers to it. And within about a year, we had a 57,000 line code called GenSam that was doing many, many different calculations at GD. Now, when did the finite element method really start? To me, in engineering, it really started around 1956. And there was an extremely important paper that was very influential that was published at that time, namely a paper of Ray Clough's in collaboration with Jonathan Turner, Harold Martin, and L.J. Top. And that paper came out of Boeing's research lab. They were very active, as were many other aerospace industries, developing finite element type procedures. Now, the name had not even been given yet. Ray Clough actually coined the term finite elements sometime in the early 1960s. Now, another seminal work on finite elements was the work of John Argyris in Europe. He divided his time between Stuttgart in Germany, where he had an institute, and Imperial College. And he published papers in the mid-1950s that were quite wonderful papers describing various ways of thinking about finite elements, the force method, the displacement method. And at the very end, you could see that he really had discovered the first, what you might call, continuum finite element, a 4-node panel element. And so these are the papers that I would say really started things going. Although it moved very, very slowly in the early years. So this is a plot that came from Web of Science, where I put in the topic finite element, and then looked at the number of papers published each year. You'll notice between 1956 and 1963, 0 papers. You find nothing. It wasn't until later that papers started to pop in. And of course, that has to do with 2 reasons. One is most people were publishing in journals at the time, in conference proceedings and a few books at the time. And not in archival journals. But the other reason was, of course, that the name hadn't come about and hadn't stuck, and that was due to Ray Clough again in the early 1960s. So thereafter, papers started to appear, and they started to grow, and they were growing rapidly, but only a little bit faster than, say, linearly over the years. But after 30 years, in 1985, there were 640 papers that year. So that took 30 years from the inception, which is quite a long time when you think about it. And if you look at the number of citations, though, the citations to the paper were growing much faster. They were growing exponentially. But they only got up to about 3,000 in 1985, again, 30 years after the beginning of the method. So remember that number 3,000. I'll come back to that when I talk a little bit about isogeometric analysis later on. So I decided that I wanted to pursue a career in research. I really loved research. And I applied to various places, but I felt the place for me and the one I really wanted to go to was Berkeley. They were active and one of the prime academic centers of finite element research, but they also had excellent mechanics and mathematics. And I had decided that's what I wanted to focus on. I would leave finite elements, patch up my background in mechanics and mathematics, and then perhaps come back to finite elements toward the end of my PhD or after I graduated. I took many courses there. And one of the reasons I was able to take so many courses and ones that I chose to take without any restrictions on my program was I had a great advisor named Carl Piester. And Carl gave me complete freedom to select my courses. There were luminaries in mechanics and mathematics at Berkeley, and I took courses from many of them. Green, Nagdi, in mathematics, Smale, Kato, Marsden, Turin, etc. I took multiple continuum mechanics sequences. I took them from Green, I took them from Nagdi, Piester. I just wanted to be very good at continuum mechanics. I had interest in solids and fluids, and of course took courses in both those areas. And also dynamics. In mathematics, I took so many courses. Lebesgue spaces, general topology, differential geometry, Lie groups, global analysis, the usual applied math courses, partial differential equations, ordinary differential equations, functional analysis classes. I took the graduate sequence in relativity. I took courses in physiology. And again, thanks to Carl giving me all this freedom. My specialty was taking the terminal sequence, the most advanced sequence, and then trying to learn all of the prerequisites simultaneously, which was quite a challenge at times. But with that, I wound up getting a PhD in engineering science. That was the program I was in. And I also had so many units in math that all I had to do is to write a brief MS thesis, and I had a master's as well in math. I have to say, I really loved my time in Berkeley. Now, my thesis was actually in arterial pulse propagation, blood flow, fluid structure interaction, topics that I've come back to in later years. And that was expressed my initial interest in cardiovascular problems. So that was in 1974. Now, my committee, during the time I did my thesis, which was actually over even less than a year, but my committee consisted of Kobe Lubliner here, who is famed perhaps in the mechanics community as his book on plasticity, Alex Turin, who's a very famous mathematician, a National Medal of Science laureate, and Stan Berger in mechanical engineering. Now, Stan was the only person on the committee that really had an intimate knowledge of blood flow. But when I needed signatures for my thesis, he had left on sabbatical, and I was not going to be able to get them in time. So we made a quick switch in the committee and put Bob Taylor on it. So he wound up signing my thesis, although he was not my advisor. I'll talk a lot more about Bob shortly, because we had a great interaction. I should say, with Kobe was a great thesis advisor. This was the old days. You didn't get a lot of direction. You just went off and you wrote a thesis by yourself and came back and sort of presented to your committee to see if it was good enough. And I met with Kobe once about 6 months into my work and told him what I was doing, just orally. And he said, "That's great, write it up." So I did. And that's how that went in those days. This is a different business nowadays. So the research I started to do at Berkeley was after I was there really about 4 years. And that was in 1973. I did my thesis, but I also started to pursue the confluence of geometry and mechanics. Again, geometry is another theme from my career. I believe it's the foundation of mechanics. I also believe it's the foundation of analysis. So we'll come back to those points. But over the next 3 years, I finished in 74, but I was a lecturer and a research engineer till 76 when I left. I worked mostly on finite element methods and structural mechanics, in addition to geometry and mechanics. And then I began my work right at the end of this time on computational fluid dynamics, CFD. So I worked on contact and impact problems, and that was the beginning of my collaboration with Bob Taylor and other topics as well. And in some sense, I think every one of them was in collaboration with Bob. Beams, plates, and shells, dynamic analysis, constitutive algorithms, and incompressible materials. I'd like to say a little bit about Jerry Marsden. I worked with Jerry on geometry and mechanics. I had taken all of the advanced sequences that were the types of mathematics that he was using at the time, global analysis, geometry, things of that nature. And he was to study, actually to teach a seminar course on the use of global analysis in fluid mechanics and nonlinear elasticity theory. So I decided to go talk to him and see what he was going to do. And I already knew more or less what he was going to do in fluid mechanics because he had written a wonderful paper on the incompressible Euler equations. And I asked him what he was going to do on nonlinear elasticity. And he said to me, "I really don't know. He said, I don't know anything about the subject. I just hope I can learn something in time." So I said, "Well, I know quite a bit about it." And I said, "I could show you that." And he said, "Well, okay, here's the deal. Why don't you just take the course and write up about 10 pages each week and give them to me on nonlinear elasticity in the language I know, which was, differential manifolds, differential geometry, things of that nature." So that's what I did. And that in some sense became the first draft of our book. We later taught a course at Berkeley on this topic. And the course was very unusual in that the only attendees were faculty and postdocs. But it went very well. That was sort of the second version. And then from there, eventually the book emerged in 1983 after I had left Berkeley. And it was republished by Dover in 94. And this is the cover of the Dover edition. So that's what we're probably most known for in the mechanics community. We wrote several other works. One was a paper on nonlinear elastodynamics. At least it started out that way. And I was interested in the well-posedness of the equations of finite elasticity in dynamics. And we were sort of stuck. We had some partial results, but we couldn't kind of take it across the finish line. And we went to perhaps the #1 analyst in the world at the time, Toshio Kato, who was on the faculty there, whom I actually sat in on a course with, and asked him for his help. And he really did help a lot and had a lot to do with this paper. But so we solved that problem, at least without boundary conditions. So it was about elasticity in an infinite domain. It was a very difficult PDE problem. But what we found out in passing was that actually it also encompassed the Einstein equations of relativity, and they were a little bit easier. You got better regularity results. So we published that. And actually this paper has sort of stuck more in the relativity community. It's often quoted as the best results for existence, uniqueness, and regularity of Einstein's equations. So from there, at the same time, really, I was working with Bob Taylor, as I said. We had a very fun relationship. We would sort of roust each other each day and go to a cafe across the street from the campus, have cappuccini, and talk about finite elements, and then sometimes come back and do a little bit of computing. And we do this every day, so this was great fun. He's a great collaborator. He's just so enthusiastic, and he's one of the most talented code developers I've ever seen. He's very famous for the FEEP platform, which is probably the #1 platform for solid mechanics research, and also for his books with Oleg Sienkiewicz. But we worked on contact impact. We were actually interested in head impact. We had support from the National Highway Traffic Safety Administration. And we also worked on very elementary plate and shell elements and beam elements. In fact, 1-point quadrature elements, the type of elements that are used for the large crash dynamics and metal forming calculations today. So this really opened up the possibility of using the lowest order interpolations and getting bending behavior. And so that paper that you see on the right sort of had a lot to do with that. And also in structural dynamics, we had a paper that I think has had quite a lot of impact over the years. It's now called the HHT algorithm, but it sort of laid out what the requirements really were for structural dynamics algorithms and produced a rather good one. It's very well utilized, especially in the civil engineering and earthquake engineering communities. So we had a wonderful period of collaboration. That ended in 1976 when I left for Caltech. But before I left, I met Ted Dolichko for the first time. I was sort of interested in some of the research he was doing and invited him for a seminar at Berkeley in 1975. And Ted presented a seminar in the morning, and then we had lunch together with Bob Taylor and Ed Wilson, and we talked about finite elements the entire afternoon. Ted and I immediately became friends. He invited me to Chicago to visit him, and thereafter just things developed. I guess what we're known most for in the mechanics community is the finite element short courses we taught around the world for about 30 years, between about 1980 and 2010. So the last short course occurred at the time when Ted had a stroke. And this was one of the flyers, the cover of the flyers from the course. So we had a lot of fun together over the years. It was just too bad that the stroke really diminished his ability to go on. So I was at Caltech in 1976 to 1980. I continued developing finite element technologies there. Some of them spilled over into the time I left, and the papers were published in, but the work was actually done then. One of the last papers, perhaps the last paper I wrote there, was a paper on fully nonlinear shell analysis. I was really taken at the time by the type of research that John Hallquist was doing at Lawrence Livermore Labs, developing finite element codes that were fully nonlinear, large deformation, nonlinear material properties, everything. And what I set out was to develop efficient shell formulations that were equally general, where you could hook them up with arbitrary constitutive equations, you could have finite deformations as well as all types of nonlinearities, contact and impact, and sort of compatible with the continuum elements. So I worked on that, and later on, when Dave Benson began to work with John, he implemented the theory in Dyna 3D, and that became really the first fully nonlinear shell formulation and element in Dyna 3D, and it led to the first full-scale simulation of car crash. And the car that was crashed was a Suzuki, and it appeared on the cover of my finite element book on the first edition in 1987. I also had the basic ideas of stabilized methods just before I left Caltech. But again, those were published later. Now, that elementary example of car crash really augured in a whole change in industry. Cars are now designed on computers. They're crash analyzed every day all around the world by every computer manufacturer. And it's a very sophisticated business. So these are calculations with LS Dyna. So in 1980, I went to Stanford, continuing my research in finite elements, but I became more and more focused on computational fluid dynamics, especially compressible flows. I was getting support in that area from various sources, and the work was immediately put into some industrial flow codes like those at Dassault, and then ultimately at Boeing as well. I continued developing stabilized methods and variational multiscale methods. And the basic mathematical theory for that was worked out by Klaus Johnson and his colleagues. And that really cracked through, and we saw how these things could be essentially mathematically designed and analyzed thereafter. And I wrote a lot of papers on that. At Stanford, I did some administration. I chaired the Division of Applied Mechanics. I chaired the Division of Mechanics and Computation, which it had morphed into, and for a short while, the Department of Mechanical Engineering. My proudest accomplishment as an administrator, and I have to admit that I was not a very enthusiastic administrator, was hiring these three individuals who became superstars in their fields of endeavor. The first was Juan Carlos Simo, whom I think everybody knows for his work in computational mechanics. Huajian Gao, who is absolutely well known in this community as a speaker, I hope. Everything goes well in a little while. And Andrew Stewart, who is now standing applied and computational mathematician. While at Stanford, the second edition of my book came out, my finite element book, the Dover edition. And I finally got out the book that Juan Simo and I had commenced many years before, but had been left dormant for quite a few years. So I was urged to get that out, finally got that out in 1998. And I think that's pretty well known in the mechanics community. The major works that I did at Stanford concerned CFD applications, stabilized methods, variational multiscale methods, and patient-specific modeling of blood flow. So in the area of stabilized methods, the first and most famous paper, the SUPG paper, appeared in 1982. A couple of the papers in a 10-part series that I wrote, it was more on compressible flows, but this one was on the Stokes equations here. It was how to circumvent the Babushka-Bretzi condition and develop stable methods that would accommodate essentially arbitrary orders of interpolation, equal order in particular. So that's had a lot of impact in analysis. It opened up a much wider range of interpolations to be used in CFD for incompressible problems. And then this paper is sort of a framework of some of the methods that we used in ultimately incompressible flow analysis, Glerkin-Least squares method. The first two variational multiscale methods, which not only explained the origins of stabilized methods, but created procedures for multiscale analysis, modeling turbulence, for example, were these two papers. And then this paper with Charlie Taylor, my PhD student, and Chris Ahrens, my colleague, was the chief of vascular surgery, was the paper that really began patient-specific modeling of cardiovascular problems. And to make a long story short, and to fast forward, Charlie and Chris eventually left Stanford. Charlie became a professor at Stanford. They eventually left in 2007 to start HeartFlow, which is a company whose main product is a diagnostic technology of coronary artery disease. And what you can do with that is you can actually calculate the pressure drops, the so-called fractional flow reserve, that is a gold standard in cardiovascular medicine. And you can do it non-invasively, just from a CT scan. Otherwise, if you do it in the traditional way, you have to insert a catheter, typically through the groin, thread it up through the aorta into the coronary arteries, and then thread it through a very vulnerable area where you have a stenosis to measure the pressure drop. So that company is now marketing this product. In fact, it was our patent, this technology, that was the first patent obtained by HeartFlow. So in 2002, after a long time at Stanford, I moved to the University of Texas at Austin. And there's a long story behind that. I don't have time to tell it. I'm often asked still, why did you leave Stanford? I'd say the very short answer is, in particular, Mary Wheeler and also Tinsley Oden. So I'll leave that as a little bit of a mystery, but Mary really started the ball rolling on that and changed my life. I've never regretted the move for a single second. So what have I been doing at UT Austin? Well, continuing with computational methods, solids and fluids, got into phase field modeling with Hector Gomez and some of my graduate students, Victor Kahlo and Yuri Vasilevs, and also then later using phase field modeling and fracture with other graduate students and my colleague Chad Landis, who's also scheduled to speak. In addition, I really started to spread out in my interest in computational medicine, continuing on work in cardiovascular disease with students and former students, and getting into prostate cancer. So we've published a few papers on that now in the Proceedings of the National Academy of Sciences, and some other areas. So I won't say anything about that because those are still works in progress, but some interesting other areas are developing in computational medicine. The signature of all of my work has been patient-specific modeling, trying to bring these technologies to use on individuals rather than just using the classical statistical and diagnostic basis of medicine. The topic I would like to talk about is the one that I'm probably most well known for during the time at UT Austin. That's isogeometric analysis. So that began here, and it is going forward to this day. The motivation came from industry. It actually came from the shipbuilding industry. But there was a report that sort of demonstrated the same problem and essentially documented a lot of evidence of the problem. And it was very comprehensive and it's well cited. It's the report out of Sandia National Laboratories that did an anatomy of the overall process of finite element analysis based on CAD representations. In other words, you have a product, you have a CAD design, and you have to build finite element models and do analysis, and then perhaps feed the results of the analysis back into the CAD designs. Well, in creating this anatomy of the process, what has been realized in many, many quarters in industry is that fixing CAD models, making them suitable for creating finite element models, accounts for a huge amount of overall analysis time, more than 80%. It's an enormous bottleneck in engineering product development. In addition, you make so many simplifications in order to generate a mesh, geometry cleanup, feature removal, that often you throw the baby out with the bathwater and you introduce a lot of new potential errors in your geometric approximation. We see that all the time. So this comes as sort of a surprise to analysts. They think, oh, this must be trivial, not worthy of our attention, creating the meshes from CAD. You have to realize real engineering designs are very complicated. So the question, though, is why is it so time-consuming? Why is this time-consuming? Let me show you a trivially simple example, and I think you may appreciate what the problem is. This is a B-pillar of a car. It's a part. It's cut out of a single piece of sheet metal. It's stamped, bent, holes are drilled in it, that's all. You should be able to generate a quadrilateral or triangular mesh on that to do shell analysis very simply, you would think, right? But that's graphics. That picture is graphics. The actual data structure in the CAD file is not analysis ready at all. It consists of mappings that are images of rectangular patches, so-called surfaces that are trimmed. And the trim lines between all of the patches are not watertight. So although this picture looks good, there are lots of gaps and overlaps between it. In this little single part, there are 1,280 such trimmed surfaces. You have to fix all that before you can generate a mesh. That's the problem. When you think of it, you scale it up to an airplane or a ship or a car, it's quite an ordeal. So the objectives that I set out were to reconstitute finite element analysis within CAD geometry. I didn't believe CAD geometry was going to be changed. That was going to be a fixed point. That was my hypothesis. But I thought I could change finite element analysis to be more compatible with that, and thereby simplify finite element model development. So what I was after was the integration of design and analysis within essentially one geometric description. And that was the genesis of isogeometric analysis. So it started with a single paper that I wrote with Austin Cottrell and Yuri Vasilevs in 2005. They were my graduate students at the time. And that paper started to get some interest, but it didn't really explode until a bit later. We also put out a book in 2009, which is an elementary introduction to isogeometric analysis. And then as time goes on, well, here is where we are in 2019. In 2019, over 13,000 citations to isogeometric articles. There are now over 3,000 papers on isogeometric analysis. If you contrast that number after 15 years for IGA versus after 30 years for finite elements, remember for 30 years, the number of citations to finite element articles was about 3,000. So this is really growing significantly. And the accumulation of citations to IGA articles as of September 22nd was over 62,000. So it's having an impact, certainly in research circles. And now it's starting to move into industry. So what is it? It's really based on the computational geometry technologies that are used in design, animation, games, graphic art, and high quality visualization. So you'll hear about things like NURBS, T-splines, U-splines. These are unstructured spline technologies. It includes the standard finite element interpolations of special cases. They become trivially simple within isogeometric analysis because the descriptions that come from these other computational geometry technologies are so much richer. So they offer you many other things. Of course, precise and efficient geometric modeling, simplified mesh refinement techniques, local or global, smooth basis functions with compact support that open up the possibilities to things like shells without rotations, phase field models, Kohn-Hilliard equations, things of that nature, very simply implemented. Superior approximation properties. There is no doubt about this. These are a more accurate basis for analysis than the traditional polynomial-based FEA. And of course, the integration of design and analysis. So from an analysis perspective, what is it? Well, I think the way to think about it, it's an enlargement of the scope of finite element analysis. You can think of it as just new finite elements in some ways. But it is also a new computational geometry technology. Some of the things that have been developed in isogeometric analysis really have a very strong design implication. But in finite element analysis, the way you get better results is you either mesh refine, that's H refinement, or you polynomial refine. You keep the mesh fixed and you increase the order of polynomials. The secret weapon of isogeometric analysis is increasing the order of the functions. They may be rational functions, they may be polynomials, but you also increase the smoothness. And the approximation properties of those are absolutely superior. And that's what we've shown. Let me show you a few examples how it solves this problem of design through analysis. You have a CAD file. This is a CAD model of an oil sump, a car part. This is the trimmed CAD file where you've thrown away all of those parts that are not part of the actual object, and you show the so-called knot lines or the mesh lines of the CAD file. It has a mesh-like structure. You can see the mesh lines are not continuous from place to place, from patch to patch. This is the untrimmed file. So this is what really is trimmed out of the CAD file. And what you do is you can work directly in that trimmed CAD file. Your analysis will take place in CAD. So this is it. Obviously, it's not a nice mesh for analysis because it has many unequal sized elements, huge elements, little elements. So to uniformize it, you can just introduce knots. It's extremely simple to refine meshes. Now you have a beautiful mesh ready for analysis, and it's embedded in the original CAD geometry. You never change the geometry. That's the power of the concept. And then you can do shell analysis. And the other beauty spot of this technology is you're still in CAD with your final analysis. So you don't have to figure out how to manually take the design changes implied by the analysis and find the CAD file and rework it. You are in CAD. Now, the 3D analog of this is the subject of immersed methods. Now, this is a beautiful CAD file. This is actually a watertight T-spline, an unstructured T-spline CAD file. And it's a surface file, but of course, this is a solid object, and you want to do a solid analysis of this, a 3D analysis. So what you can do, in the same spirit as the previous example, is drop this into a box of B-splines, throw away all of the Bezier elements of the B-splines that don't intersect the object, do local refinement where you need it, and use this immersed technology now with cut elements to solve the problem. This is just a quadrature mesh over here. And then you get a 3D analysis. You can fully automate that process. It so simplifies things, it's just amazing. And I think the next example will illustrate to you the degree of simplification that can be shown with these isogeometric methods. This is the original dirty CAD model of some type of a very complex bracket. Dirty CAD models are typical. They have gaps and overlaps. And before this was subjected to healing software, it had 3,361 edges that were not coincident. They were not watertight, so there were gaps and overlaps. Now, healing software helps a lot, but this is really a complicated little gizmo here. After healing, there were still 250 edges that were not watertight. So you have to fix all that, and that has to be done essentially semi-manually before you can generate a mesh. And to generate a solid mesh for this would be a nightmare under any circumstances, even with the best mesh generators. But again, what you can do is just drop it into a box of B-splines, throw away the elements that don't intersect the object, and perform three-dimensional analysis, linear and nonlinear. And the further interesting thing about this technology is you don't even have to do any mesh healing. Those gaps and overlaps are very tiny, they're very small, and you can take care of that in the process of solution. It's no problem whatsoever. So you can do essentially automatic 3D design through analysis computations like this. So it's a technology that's continuing to be developed, and it's having its impact. But let me contrast its trajectory in the world with finite element analysis. Finite element analysis started primarily in industry, in the aerospace industry. It migrated from there to academia, and then to other disciplines, civil and mechanical, etc. Commercial CAD and FEA software, the industries grew up completely separately. They just didn't pay any attention to each other, and that created the problem. And IGA was really a look back at the problem and a response to industry needs. But it started in academia, in my group at UT, and it has been migrating from there to industry. And now more companies are starting to pick it up and put it into service. And for example, it's been pioneered by LS China and LST Software before it was acquired by ANSYS. Now it's part of ANSYS. That they pioneered IGA software in industry. So it's still a work in progress, but it's expanding rapidly, and it's still an exciting area of mathematical and computational mechanics research. So with that, let me just sort of sum up with my philosophy of what it is I do as a computational mechanician. What do we do that's different from what people do traditionally? Well, what I did is I translated some words of Leibniz, and it really concerned his philosophy, which I think is really the philosophy of a computational mechanician right now. What he said is, what I most desire is to perfect the art of inventing in general and to create more methods as solutions to many problems, since a single method comprises an infinity of solutions. And I think that's really well said. I mean, this is a man who is the co-inventor of calculus, which is a method, and you can see the impact of that. So I think this is what we do, and I think we do have great impact, but it's a confluence of mechanics first, computation second, and mathematics, all of those things together. So with that, I will thank you very much for your attention. I'm looking forward to the next 50 plus years in mechanics and computation, and looking forward to my colleagues and their talks that will follow. Thank you again.
Thank you, Tom, for having the conference with a very inspiring talk on the major milestones in your career path and how it helped you shape the technological developments. I think we have a few minutes, so I will open the floor for questions. There is one question from the audience, and I will read it out for you. You mentioned that the research and teaching environment has changed considerably over the years. What would you do differently if you were to start in the field of computational mechanics today?
That's a good question. You know, I don't think you can really answer that in a totally honest way, because your path in life sort of dictates when you make decisions. I didn't even know anything about computation until I got to General Dynamics. And actually, it was the interview that intrigued me to go there, because they were doing things in the area. And so that's how I was able to think this is something I really want to do. But, you know, you can't you can't go back and say you live your life over. It doesn't work that way. You know what Yogi Berra, the great philosopher, says, you know, you come to a fork in the road, you take it. So it just unfolds. So it's impossible to say what I would do differently. I'll tell you though, as I said, I loved Berkeley, and I think it was the perfect spot for me at the time, because all I did is take mathematics and mechanics classes and a few other topics that I was interested in, like relativity and physiology. But it gave me a very strong background and the ability to pursue different questions as they arose over the years. And I wasn't even sure that I was going to get back into finite elements. There was another fork in the road. Was I going to go all the way into mathematics? I'm not going to do that. So that was a decision I made, and I think I'm happy with that, the decision too. The decision is I kind of walk the tightrope in between, you know. And when mathematics is getting too complicated, I do engineering and mechanics, and when they're getting too complicated, I do some mathematics, you know. So.
Thank you. I see that there are two. We'll go with Glacio Polino. Glacio, you have a question, and then we'll go with Yugang.
Yes, I do. Can you hear me?
Yes.
A little bit.
Great. Tom, great lecture. I really enjoyed it. And I really appreciate your selection of the topic because what you did is something that we cannot find in any book or paper. And now we have this lecture documented. This is one of the advantages of the COVID that allowed us to have this great lecture. Of course, COVID is bad, but what I mean is the virtual conference enabled this great lecture. And if I would choose one word to define your lecture, I would say inspirational. You inspired me a lot, Tom, with your lecture. And I have a question. Tom, what called my attention a lot was the coffee that you had with Bob Taylor at Berkeley. Because such a spontaneous event can be the catalyst of a tremendous creativity, as your work demonstrates. And as you know, I am working on the virtual element method. Oh, we lost Tom?
No, I think he's on the stage. I think you can continue your question. He'll be able to listen.
Okay.
We have Yugang also for questions.
Yes.
So
I was going to mention to him is a nice story that I have been working with Franco Bretzi, and he told me a story that he and Tom were on a coffee at Texas, and then the waitress came and so they were discussing and working on napkins, and then the waiter told them, gentlemen, hyperbolic PDEs, huh? And the waitress was a math PhD student at the Texas Austin. So my question for Tom is, can he elaborate a little bit more on the coffee with Bob Taylor and on the importance of events such as these events he had with Bob, and the importance of these events to catalyze great ideas and great scientific advances?
okay, Tom, are you there? I think there's maybe some computer glitch. Yugang, can you please pose your question as well? So as Tom comes back, I will repeat both the questions.
Sure. I'd like to ask Tom his vision of competition. Tom, my question is that what's your vision of computational mechanics in the next 50 years?
Okay, let me just start with that, because I think it's obvious right now we're seeing this advent of machine learning. So how that influences computational mechanics, you know, there are people that perhaps are maybe overhyping it because they say it will solve all problems of humankind. But I think in fact it is going to have a big impact. And what we need is a proper synthesis of it with modeling and analysis. And there are people that are endeavoring to do that. But you know, that's about as far off into the future as I can see. The other thing I would say, if quantum computing comes to the point where we can really start computing something interesting. That could be a big game changer, and probably will be, but it's still too early for that. Let me come back to Glaucio's comments, because I have a lot to say about that. First of all, Glaucio, now you have to give a lecture on the advantages of COVID, or write a book like that. That will be a surprise, I'm sure, to hear about that. I think actually, unfortunately, COVID, it does just the opposite, because all of these things that are the basis of collaborations are much more difficult, of course, with COVID. But, you know, you mentioned Franco. I didn't talk about him in the lecture, but I could have. It was more a mathematical lecture, I probably would have. But the people that I've worked with over the years are people that I actually became friends with before I really started working with them. I met them through science, but I became friends with them. And it was just being together that led to our collaborations. That was true of Jerry Marsden, Bob Taylor, Franco, many of my graduate students. I still work with a lot of them because they became my friends. So I think, you know, you want to work with, you want to be around people you like, and that's the basis of collaboration, really. Obviously, they have to be bright and doing something interesting, but it's friendship. It's the basis, really.
Thank you.
I enjoyed Bob Taylor. Whenever I see Bob Taylor, I love Bob Taylor. And you know, unfortunately, we lost Jerry. That was a big loss. But Jerry and I became friends. I mean, we immediately just started to, we lived near each other. We each had houses together. You know, we had kids that are at the same time. We would do things together. And the work was kind of just part of the friendship.
Thank you all. Thank you very much. And this brings us to the end of the hour. So let's thank Professor Hughes for a very inspiring talk and starting the virtual conference. Thank you very much. So now we have the Eringen Medal Symposium that will start immediately. So we'll be back in a couple of seconds. There are 15 talks back to back with no break in between. So I will request all the speakers to kindly stick with the 10-minute rule so that we can set you up and bring you up. You will hear a sound of bell at minute 10, and then I will come up to the stage to help you wrap up. So we'll be back in a few moments. Thank you.